Assalamu alaikum. My name is Sayed Kashif and I'm from chemistry department and this is a chemistry presentation. The topic of today's presentation is sodium ion battery. So we will discuss about the sodium ion battery in detail. Moving towards the next slide. So first of all, we will see the contents. What is sodium ion battery? What it exactly looks like? What is the motive behind it? What are the specification? What are the properties of the sodium ion battery? Research development on sodium ion battery. What is the current research going on in the sodium ion battery as it is a developing technology? What is the construction? What is the basic needs to construct a battery? Working advantages. What are the disadvantages of the sodium ion battery? What are the applications? What are the uses of sodium ion battery? And then finally, we will conclude and we will discuss about the future perspectives of the sodium ion battery. So let's start our presentation. So what is exactly a sodium ion battery? The sodium ion battery, it is a type of rechargeable battery that uses sodium ions as its charge carrier. So basically, the sodium ion battery uses sodium ions to carry its charges and it is a type of rechargeable battery. Its working principle and cell construction, they're almost identical with those of lithium ion battery as we are familiar with the lithium ion battery. But just we wish we will replace the lithium with the sodium. The sodium ion battery is relatively young compared to the other battery types. The battery grade salts of sodium are cheap and abundant, much more than those of lithium. So this was a description of a sodium ion battery. Then moving towards the next slide. This is a high voltage sodium ion battery. The right side of the picture shows the cathode and left side of the picture shows us the anode. From the anode, the electron are transferred to the cathode and so on. The sodium ion battery works as this way. So this was the description of the sodium ion battery. Let's move towards the next slide. Specifications. What are the properties of sodium ion battery that the research is going on the sodium ion battery? Imperviousness to temperature changes, such that it can resist the temperature changes. Stability, it is a stable one. It has a long life cycle. This is the one advantage over the lithium ion batteries, as the lithium ion batteries age very fastly, so it has a long life cycle. The round-trip energy efficiency of sodium-ion batteries is 92% at a discharge time of 5 hours, in contrast with a lead-acid battery that has an energy efficiency of circa 70%. So, energy efficiency of sodium-ion battery is more than the lead-acid battery. The sodium battery cells can be manufactured using the current cell production equipment, which will help keep the costs down. A hybrid mix of 40 kilowatt per hour sodium ion batteries and per kilowatt per hour lithium iron phosphate batteries would be per kilowatt hour for the overall pack. So the sodium ion batteries can be used for a broad range of battery applications. This is the only reason that research is going on the sodium ion battery so extensively. These factors, price, abundance, size, make sodium ion batteries particularly interesting for large-scale grid storage applications. So these were the specifications of the sodium ion battery, the properties of it, and let us move towards the next slide. This picture shows the description of the sodium ion batteries, that longer lasting sodium ion batteries. This is a major advantage over the lithium ion batteries. So let us move towards the next slide. So research development on the sodium ion battery. What is the research motive? What is the research going on currently in the world so that then a sodium ion battery should be commercialized in the industries? The sodium ion battery technology is just developing right now. Efforts are being made to select the positive electrode and the negative electrode on the basis of the efficiency of the whole game is based upon the choose upon the positive electrode and the negative electrode. This is because the sodium ion batteries will depend on the positive electrode and the negative electrode. Research is being made on how to apply the appropriate materials for electrodes and how to use it instead of lithium ion batteries in the future, near future. So moving towards the next slide. Positive electrode materials. So we will distinguish it between the positive electrode materials and the negative electrode materials. The first one is the iron and manganese based layered oxide. The manganese based materials, more preferably iron based materials, they are used because the elemental abundance in the earth's crust, it is relatively high and therefore low cost. Iron and manganese based electrode materials as the sodium insertion host therefore provide great advantages in applications for large scale batteries, especially electrical energy storage systems. So this was the description of a positive electrode material which can be chosen. Moving towards the next slide. This is a description of the iron and manganese based oxide, manganese based layered cathodes, positive electrodes. As it has a natural advantage of abundant source and a low cost. Electrochemical properties are high voltage, high energy density, fast opacity fading, large polarization. What are the challenges and issues? Thus, iron migration, structural degradation happens, and the oxygen evolution side reaction often occurs. So this was a description of the iron manganese based layered oxides. Moving towards the next slide. O3 NaCrO2 as an electrode material. An important finding of O3 NaCrO2 as an electrode material is the thermal stability. It is a thermally stable one. A study on the thermal stability of Na0.5 CrO2 by accelerating the rate calorimetry has revealed that Na0.5 CrO2 is surprisingly more stable than the LIX FePO4 as one of the most thermally stable electrode materials. The electrode performance of O3 NaCrO2 at elevated temperatures such as 80 degrees Celsius. It has been recently reported in pure ionic liquid, alkali metal, sodium and potassium ions as cations and bisamide FSA as an anion. And excellent cyclability and rate capability have been demonstrated. No structural degradation and long life cycle at elevated temperature are at a consistent result with the excellent thermal stability as an electrode material. So this was one of the electrode material which is the positive electrode material which can be used. So let's see what the next slide says. O3/P2 layered oxide, especially O3 NaCrO2, have been widely investigated as cathode materials for sodium ion batteries due to their high stability and flexible synthesis procedure. But their low electron conductivity, the toxicity of chromium 4, 6, and cation disorder limit their applications. Moving towards the next slide. This is a graph of the previous slide, which can be described as the current capacity. The side where the y-axis shows the voltage and the x-axis shows the capacity, the current it can carry out. So moving towards the next slide. Sodium transition metals, oxides. Owing to their high tap density, high operating potentials, and high capacities, cathodes based on sodium transition metal oxides have received the greatest attention. To keep costs low, research attempts to minimize costly elements such as cobalt, chromium, nickel, or vanadium, a P2 type of Na2/3Fe1/2Mn1/2O2 oxide from the earth abundant iron and manganese sources can be reversibly stored 190 milliampere H/G at average discharge voltage of 2.75 volts as sodium plus utilizing the Fe3+/4 plus redox couple on par or better than commercial lithium ion cathodes such as LiFePO4 or LiMn2O4. So this was the sodium transition metal oxide description, as it has the advantage over the commercial lithium ion cathodes. So moving towards the next slide. Polyanions. Polyanions can also be used as a positive electrode material. Research has also considered cathode based on polyanions. Such cathodes offer low tap density, lowering the energy density on account of the bulky anion. This may be offset by the stronger covalent bonding of the polyanion that positively impacts cycle life and safety. Among the polyanion-based cathodes, sodium, vanadium phosphate, and fluorophosphate, they have demonstrated excellent cycling ability, and in the latter, an acceptably high capacity 120 milliampere H/G at high average discharge voltages 3.6 volt versus the sodium/sodium ions. So this was the description of the polyanions. Moving towards the next slide. So this is a short description of polyanion type electrode materials. It can contain pyrophosphates, fluorophosphates, silicates, sulfates, carbonophosphates, and the phosphates. So it can have a variety of phosphates. So moving towards the next slide. So now we will discuss about the negative electron materials. One thing I would like to mention is that the whole positive electron material and the negative electron material description is taken from a article. I have gone through many articles, and this was the best description that I found, so I put it into the presentation. Sodium insertion into the hard carbon. Sodium ion batteries use hard carbon, a disordered carbon material consisting of a non-graphitizable, non-crystalline, and amorphous carbon. Hard carbon's ability to absorb sodium was discovered in 2000. This anode was shown to deliver 300 milliampere H/G with a sloping potential profile above 0.15 volt versus sodium/sodium ions. It accounts for a roughly half of the capacity and half potential profile, a potential plateau below 0.15 volt versus the sodium and sodium ions. Graphite anodes for lithium ion batteries offer typical capacities of 300 to 360 milliamperes H/G. The first sodium ion cell using the hard carbon was demonstrated in 2003 and showed a 3.7 voltage average voltage during the discharge. So the hard carbon is preferred due to its excellent combination. These are the advantages of using the hard carbon. It has excellent combination of capacity, lower working potentials, and cyclic stability. So this was the description of the sodium insertion in the hard carbon, which is a negative electron material. Moving towards the next slide. So this is a short description of the hard carbons. With the discovery of the hard carbon as more suitable anode material and increased demand in large-scale stationary electrical energy storage, progress towards the commercialization of room temperature sodium-ion battery, it has seen increased transactions. So hard carbons, it has electrodes for sodium-ion batteries. It has high capacity, low working voltage, low cost, and as you can see on the screen. So moving towards the next slide. Late structure of MOS2. This is the latest research that I have put in this presentation. In 2021, researchers from China, they tried the late structure MOS2 as a new type of anode for the sodium ion batteries. A dissolution recrystallization process densely assembled carbon layer coated MOS2 nanosheets onto the surface of polyamide derived and doped carbon nanotubes. This kind of carbon MOS2 /NC NTS anode can store 348 milliampere at 2 ampere per gram with a cycling stability of 82% capacity after 400 cycles. TIS2. TIS2 is another potential material for sodium ion batteries because of its layered structure, but has yet to overcome the problem of capacity fade. Since TIS2 suffers from the poor electrochemical kinetics and relatively weak structural stability. So this was the description of the negative electron materials, layered structure MOS2, MOS2 and TIS2. So moving towards the next slide. So we will basically talk about the construction. A battery should be constructed well, and if not, it will not perform efficiently. A typical sodium ion battery consists of anode, cathode, electrolyte, and a separator. The operation is similar to that of lithium-ion batteries. Different electrolytes can be considered for a sodium-ion battery, such as ethylene carbonate, EC, diethyl carbonate, propylene carbonate, dimethyl carbonate, ethyl methyl carbonate, butylene carbonate, and vinylene carbonate, and salt combination LiPF6 and NaClO4. So this is a short description of the construction. It has an anode, electrode, cathode. The electrons move from the anode and gets discharged at the cathode, so the batteries can be charged. So moving towards the next slide. So we will talk about the working principle of the sodium ion battery. What is the philosophy behind the working principle? In sodium ion batteries, the sodium ion is shuttled between positive cathode to negative anode during the discharging/charging. During the charging process, the sodium ions from the cathodes are extracted and inserted into the anode. The electrons are pushed from the cathode to the anode through the external circuit during the charging process. The reverse is true for the discharge process. So it is. So this is a short description, anode, cathode, and of the working principle of the sodium ion battery. So moving towards the next slide. So we will talk about the advantages of the sodium ion battery. What are the advantages of the sodium ion battery? First of all, it is rechargeable. Sodium ion batteries for energy storage. It is easy to recycle, low market prices, capable of working at room temperature, good efficiency. It has an enhanced safety, better raw material costs than the lithium ion. These were the short advantages of sodium ion batteries. Moving towards the next slide. What are the demerits? What are the low points where the sodium ion batteries are lacking? What are the drawbacks? Large ionic size of sodium plus, which require more power to keep energy flowing. It takes several days to charge in case you forget to charge it full. Lower operating voltage, lower energy density. It needs high temperature for the optimal work. So these are the some disadvantages of the sodium ion batteries, and the research is implemented on how to get rid of these disadvantages. So in the next slide, we will talk about the applications. What are the applications and what are its uses? First of all, automobiles and transportation. The carbon emission reduction goal has a significant effect on the transportation electrification. So cost-effective battery chemistry, it is highly needed as electric vehicle sales are expected to grow in the coming years. Sodium ion battery, it is an undeniable choice for the electric vehicles, so that it would be adopted, you like or not. Grid level applications. Smart grid rely on the reliable power. The intermittent power supply can impede grid functioning. The sodium ion batteries can help optimize the solar energy and wind energy to effectively meet unique grid energy requirements. So we will what we are going to talk about industrial mobility. Sodium ion batteries can maximize the asset utilization and minimize the operating costs with the constant red lines and powerful peak power. So this was the description of the application. What are the uses where it can be used? Moving towards the next slide. So finally, we have come to the point that we will finally conclude it, and the future perspectives. What are the future perspectives taking into consideration of the sodium ion batteries? So research activity on sodium ion battery materials, it has increased significantly in past decade, with a key motive behind this search is to find reliable, safe, and cost-effective substitute of lithium-ion batteries. Most of the research carried out on lithium-ion based systems, it has been successfully transferred to sodium-ion batteries to explain and improve the fundamentals of various physiochemical, electrochemical phenomenon within the battery system. Nonetheless, there are some key differences in the electrochemical behavior of both battery systems. That, for example, cell voltage of sodium half cell is lower than lithium by 0.3 voltage, whereas sodium ion conductivity, it is higher than lithium ion due to its polarizability. Based on the so finally discussing the last point, based on different performance parameters, sodium ion batteries, they have the potential to compete with the lithium ion batteries on these three main areas of application, starting from the small to medium range and finally large scale application, that is portable electronic devices, electric vehicles, and electric grid systems. So this was the conclusion of my presentation, and I discussed about the future perspective of the sodium ion batteries. These are the references from which I took the material and put it in the presentation. Thank you so much. I hope you will like this presentation. So this is Sayed Kashif signing off. Take care. Allah Hafiz.